We're going to finish up Chapter 9, talking about 9.3, partitions of integers, and obviously how we use generating functions with partitions. Let's recall what a partition is. It's an unordered arrangement of integer summons that add to the integer. So for instance, if I'm looking for integer partitions of 1, 1 adds to 1, and that is it. If I'm looking for integer partitions of 2, I could use just the number 2, or I could take 1 plus 1. For 3, I could take 3, or I could add 2 plus 1, and I want you to understand that that's the same as 1 plus 2, because order doesn't matter, so we're not going to say those are unique, those are the same. 2 plus 1 or 1 plus 2. And then I could say 1 plus 1 plus 1. And you can see I continued for 4, or 3 plus 1, or 2 plus 2, or 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1, etc., etc. So the way that we then notate that is P of 1, which means the number of partitions of 1 is 1, because there's only one partition. And P of 2 would be 2, and P of 3 would be 3, and P of 4 would be 5, and P of 5 would be 7. Now, if I asked you what's P of 32, well, that would be much more time consuming. So what we want to do is look for a way to do this with generating functions. Essentially, how we do this is we look at how many ones would I use. So how many ones? Well, that generating function would be that I could use 0 ones, which of course x to the 0 is 1. I could use 1 or 2 or 3, etc., all the way to infinity until whatever n is that I'm trying to solve for. How many 2's? Again, I could use 0 2's. And remember, I'm going to go straight to x squared here because I want my exponent to represent the value. So I wouldn't use x to the first, even though it's 1, 2, I'm really adding 2 values. So 2, 4, 6, etc. 3, 6, 9, or 0, 3, 6, 9, etc. for 3's, and we can see how this pattern would continue. Looking back at how we then wrote each of these generating functions, this would be 1 over 1 minus x. That was just that fundamental identity from section 9.1. If it was going by 2's, it was 1 over 1 minus x squared, 1 over 1 minus x to the third, etc. And you can see that it would be essentially all the way up to 1 over 1 minus x to the n. So whatever I'm doing, it's really just going to be 1 over 1 minus x times 1 over 1 minus x squared times 1 over 1 minus x to the third, etc., all the way to 1 over 1 minus x to the n. And that's how I'm going to find the number of partitions of n. So again, the number of partitions of n would be exactly what we just went through, which is writing all of this, and this is where I would end up. Now, previously we learned summation notation. Summation notation means add up whatever values that you have. So we're very familiar with summation notation. This might be a new notation for you, perhaps not. This is essentially the same thing as sigma, but this means product. So it's a pi product, and essentially I'm saying go from where x is 1 to where x is infinity. So I could write it I equals 1 to infinity, or note I just wrote I is greater than or equal to 1 because it implies that it keeps going forever. And I'm taking 1 over 1 minus x to the I. And so essentially that's saying the same thing as this. It's saying take the product of all of those values until you get to n. Again, it doesn't makes sense for us as humans to calculate the pi product, just like I would let you keep your answers in, your binomial coefficient notation previously. All I want you to do is come up with the pi product, because computers can calculate that in a snap. Looking at the same concept, what if I wanted to determine a generating function for a sequence where an is the number of partitions of non-negative integer into even summons, which meaning I'm looking for only even values? Well, we can tell that instead of x0, x1, x2, I would be going straight to x2, x4, ... and then if I went by 4s, and then if I went by 6s or 8s or 10s, etc., again, I'm looking at something that looks like this. So I'm only looking at the even values. Again, how would I write that with my pi product notation? Again, you can either write it this way with the pi product, or I could have used the same that I used before, I is greater than or equal to 1. But notice what I've done here is I've basically said it's going to be even because I'm going to take I times 2, so that's only going to give me even values here. Let's change it up yet again. Now this one is asking about distinct summons, which means I don't want to have something like this where I've used 1 more than once, or 2 more than once, or 1 more than once, or 1 more than once. So looking back at the partitions of 5, even though P5 was 7, if I'm looking at the distinct partitions, P sub D, telling us that it's distinct, of 5, there are only 3 of them: 5, 4 plus 1, and 3 plus 2. So my question now is, can I generalize this for n? So can I write something where P sub D of n is equal to something general? Can we generalize that for P D of n? We're saying, can we generalize? We're looking at distinct summons. So if we think about distinct, we're basically saying I'm going to use a 1, or I'm going to not use a 1. I'm going to use a 2, which would add 2 to our sum, or I'm not going to use a 2. I'm going to use a 3, or I'm not going to use a 3. So we get the idea that that pattern would continue. To write it as a pi product, I'm going to write it as the pi product of 1 plus x to the I. So again, I'm multiplying 1 plus x to the first, 1 plus x to the second, 1 plus x cubed, etc., etc., all the way up to whatever value I determine that I'm trying to solve for. Here's an integer partitions question for you to try on your own. I'm asking for the generating function, again, write it as a pi product, don't evaluate, for the sequence where a sub n is the number of partitions of non-negative integer n into distinct even summons. When you are ready, press play to see how you did. Again, so we're looking for distinct and we're looking for even, so we're kind of putting two things together that we've already sort of talked about. Again, for each partition, we're either going to use the summoned or we're not, which we can model using 1 plus x to the 2k. So why did I choose 2k or 2I or whatever letter I choose? Again, here I used I, so in my final answer I used I. Why did I use 2? Because we're looking for even summons only, so I'm looking for x squared, x to the 4th. Again, not using 6 or using 6, not using 8 or using 8, etc., etc., etc. That is how we're going to write that pi product. Here's a very common application of integer partitions. Let's say I'm trying to find the number of integer partitions for a plus 2b plus 4c, and again it would be 1a, 2b, 4c equals some number. So my question is, how many a's will I use? Well, a's go up by 1, so notice I'm just having my exponent increase by 1, which I can write as 1 over 1 minus x. For b's, that will increase by 2. Remember, I can write this as 1 over 1 minus x squared. For c's, each time it will increase by 4. So that's 1 over 1 minus x to the 4th. So my solution is whatever n happens to be of this product. So here's another to look at. 27a plus 42b equals 192. What's the number of integer partitions? Well, I know that I'm looking for x to the 192, which means the coefficient for when x is equal to 192. I'm sorry, when x is to the 192nd power. How would I write this? Well, I can write this out as x to the 0 plus x to the 27 plus x to the 54, etc. Oops. Plus dot dot dot. For 42, it would be x to the 0, x to the 42, x to the 84, dot dot dot. But really, I don't care about that line of work. What I really want is, how am I going to write this? Well, that's 1 over 1 minus x to the 27. And this is 1 over 1 minus x to the 42. And again, that's all I have to do. I don't have to work anything out. I just have to write it symbolically. Here's a first question for you to try on your own. Again, I'm looking for, in this case, the number of ways an advertising agent can purchase n minutes of airtime if time slots for commercials come in blocks of 30, 60, or 120 seconds, and we're going to assume that 1 unit of time is 30 seconds. Try this question. When you are ready, press play to see how you did. So where I would start is I would write this equation. So let's talk about this equation first. If 30 seconds is 1 unit of time, then if I let A represent each 30-second slot, then it would just be 1A, because that's just 1 unit of time. If B is 60-second slots, then obviously that's 2 units of time. And if C is 120-second slots, that's 4 units of time. The question is then, why is this 2n if I'm looking for n minutes? Well, we're looking at n minutes, but this is 30 seconds, and so obviously I need to take 2 times n to get the number of minutes, since there are obviously 60 seconds in a minute. So that is my initial equation. If you weren't able to come up with that equation, you weren't able to finish this question, and that's okay. But remember this one, because the last practice will be a continuation or an alteration of this question. So again, the number of 30-second blocks, 0, 1, 2, 3, etc. The number of 60-second blocks, remember I'm only going to be using those even exponents, because that's going to give me 2 units of time, or 4, or 6, etc. For 120, I'm going to be going by 4s. And then again, because my solution to the equation is 2n, then I'm looking for the coefficient of x to the 2n. I'm taking each of these and just rewriting them. This is 1 over 1 minus x. This is, because I'm going by 2's, 1 over 1 minus x squared. And then again, because I'm going by 4's, 1 over 1 minus x to the 4th. So here is my final solution. It seems so easy once you go through it, but again, keep this equation in mind, as we're going to use it again in just a moment when we try practice 3. One last question to try together before I have you do a similar question on your own. Let's take a look at what happens when I add some additional restrictions. So this should look familiar to us. where we have a plus 2b plus 4c is equal to n. And now I'm saying, but, hey, b has to be greater than or equal to 2, and c has to be greater than or equal to 3. So let's take a look at each one of these. Now for the number of a's, that one's very straightforward. I didn't change anything. The coefficient is still 1, so it's 0, 1, 2, 3, etc. For b, remember previously for b, I had used x0, x2, x4, x6, etc. because I was going by 2's. Now I'm saying b has to be greater than or equal to 2, which means if I plugged a 2 in over here, that's actually 4 is my very first value that I could use. So really I'm looking at x to the 4th plus x to the 6th plus etc. 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 So that's for the number of b's. Similarly for c, previously I had x to the 0, x cubed, x to the 6th, x to the 9th, da da da. Now I'm saying, oops, I better keep going just a little bit, x to the 12th, x to the 15th, da da da. And now say 3 times 4 is 12, so 12 is the first one. So I have x to the 12th, x to the 15th, etc. on forever for the number of c's. From here what I want to do is kind of put this all together, but keep in mind that while I can still rewrite this as 1 over 1 minus x, this is now going to be an x to the 4th taken out, and then I will have 1 plus x squared plus x to the 4th, which can be written as x to the 4th over 1 minus x squared. So the x to the 4th that I have factored out, and the 1 minus x squared because I'm increasing by 2. And same concept here, I'm going to take out x to the 12th, and then I would be going up by 4's. And so to simplify that, that would be x to the 12th over 1 minus x to the 4th. The next step then would be to essentially write it as a generating function. So I'm trying to find x to the n because that's the solution to my equation. And what do you suppose is going to come next? Well, I've got 16 x's. So really, this is x to the n, and then I've got x to the 16th times 1 over 1 minus x, 1 over 1 minus x squared, 1 over 1 minus x to the 4th. Just as we did before, I'm going to sort of smush those two together and say, let's go ahead and shift it back. So now I'm looking for x to the n minus 16 of all of this because I've shifted it by 16. Here is your last practice, tied very closely to practice 2 that we did already. The only thing I've changed now is I've given you some restrictions. He must purchase at least 2 30-second blocks and at least 3 120-second blocks. Everything else remains the same. So see if you can incorporate what we just talked about with the further restrictions into this question. When you're ready, press play to see how you did. So what hasn't changed? This guy hasn't changed. That's the same equation we came up with before. This is 1 block, 2 blocks, 4 blocks. We said it had to be 2n because n was number of minutes of airtime, and so we would need 2 30-second units to create 1 minute. So that part did not change. Number of 30-second blocks, it says he must purchase at least 2 30-second blocks. So notice this guy did change. That is now x starting with x squared, which means again that what I would do is take out an x squared to get that x to the 0 as the first value, which means I would be writing that as x squared over 1 minus x, which is where I got this value. For number of 60-second blocks, this one did not change. No change at all. So we're looking at 1 over 1 minus x squared. oops, not x minus x squared, I apologize. And that's this value. And then for 1/22 blocks, I need at least 3 of those. So again, I'm looking at getting rid of the first 3 values, which is x to the 0, x to the, because we're going by 4 units, and x to the 8th. So that's where I'm starting with x to the 12th. So 12, 16, 20, etc. Just as I did before, I'm going to factor out, in this case, x to the 12th, so that I can have x to the 0 as my first term, and now I'm increasing by 4s. So that is rewritten as x to the 12th over 1 minus x to the 4th. Like I did in my last example, I'm going to consolidate my x's, so this is really x to the 14th in front of all of this, now with 1s as the numerators. And so essentially I've just taken the minus 14 and basically subtracted 14 from 2n, and that is going to give me the expression that I need.